everyone, welcome to this explainer. Today we're diving straight into the nuts and bolts of foundational IT infrastructure. If you've ever wondered what actually goes into building a network from the ground up and why traditional bare metal setups have these inherent limitations that drive modern software engineers absolutely crazy, well, you're in the right place. We're going to look closely at the architecture of legacy systems to truly understand the physical and financial realities of on-premise computing.
Here's our roadmap for this explainer. First, defining traditional computing. Second, real-world architecture. Third, cost and maintenance burdens. Fourth, the scalability problem. And finally, the cloud shift.
All right, Section 1, defining traditional computing. To really grasp modern engineering, we first need to understand the exact environment developers have been struggling with for decades. So the crucial point here is that traditional computing requires you to physically own everything. It's an on-premise model. This means an organization has to front a massive amount of capital to buy, assemble, and manage their own physical bare metal infrastructure. You aren't just renting digital space somewhere. You're buying the actual hard drives, the processors, literally miles of cables, and you're physically installing them inside your own building.
Moving on to Section 2, real-world architecture. Let's ground this theory in a scenario you'd actually see in the real world. Imagine a college or a growing company that needs to set up an enterprise resource planning, or ERP, application. Just to get that one single app up and running, they are looking at a massive initial investment. They need physical servers and client terminals. They have to run complex network cabling. They absolutely need uninterrupted power and heavy-duty cooling systems, because without them, a server room basically turns into a sauna and the machines literally melt. And on top of all that, they have to pay recurring salaries for a dedicated in-house IT team just to keep the lights blinking. When we look at a conventional computing setup, the application sits right on top of an operating system, and that OS is tightly coupled to highly specific physical hardware resources. We're talking about the processor, the memory, and the disk forming this absolute concrete foundation. In this traditional model, the software is rigidly bound to that specific piece of hardware, meaning if that physical disk goes down, your application crashes right along with it. What this creates is a highly rigid stack made up of three layers. First, you've got the infrastructure, which is your bare metal physical devices and power. Second is the platform, which is that hardware loaded up with your OS. And third, you have the application itself. Because these three layers are so rigidly stacked and dependent on one another, application developers and everyday end users often get dragged into the totally frustrating, time-consuming mess of managing the underlying infrastructure. So instead of just writing code or doing their jobs, developers are suddenly stressing out over hardware patches and server maintenance. Section 3, cost and maintenance burdens. It's pretty easy to see how this rigid architecture immediately kicks off a chain reaction of business and engineering headaches. These limitations compound really quickly. Not only are you dealing with that huge initial capital investment and the recurring administrative costs, but you are also fighting a losing battle against time, because hardware gets outdated incredibly fast in the tech world. Hardware failures cause totally unpredictable downtime. And honestly, the worst part? If your business actually grows and you need to expand your capacity, you literally have to shut the entire system down just to install the new servers. It really makes you ask, how do we avoid these massive investments and those inevitable service disruptions? Section 4, the scalability problem. That risk of service disruption brings us directly to a fundamental engineering concept, which is scaling. Scaling is essentially a system's ability to grow or shrink based on whatever the workload demands are at that moment. In traditional computing, you basically have two options. First is vertical scaling, which means upgrading the quality of your existing hardware to increase speed, like swapping in a much better processor. Or there's horizontal scaling, which is adding more physical hardware nodes to handle simultaneous traffic. If we use a highway analogy, vertical scaling is like paving the existing lanes with better asphalt so cars can drive faster. Horizontal scaling is like buying up the land next to the highway to widen the road entirely and add more lanes. The big problem here is that in a traditional hardware environment, both of these are incredibly difficult, wildly expensive, and completely static. The ultimate flaw of this static capacity is the massive waste of resources. Think about having a fixed amount of resources that you've purchased and allotted to your application. Now, compare that to the actual, real-world demand from your users over time, which constantly fluctuates. When demand spikes above your allotted resources, you hit under-provisioning. Your servers get totally overwhelmed and the system crashes. But what about the valleys? When demand drops way down, you are over-provisioning. You end up with these expensive, power-hungry servers just sitting there idle, basically burning money. Section 5, the cloud shift. Recognizing this massive inefficiency sets the stage perfectly for the evolution of the entire IT industry.
This brings us to the modern solution, cloud computing. Unlike traditional computing with its huge capital expenses and rigid hardware, the cloud treats computing like a public utility. Think about how you use electricity. You don't build a full power plant in your backyard just to run your refrigerator, right? You just plug it into the wall and pay for exactly what you use. Cloud computing does the exact same thing for IT. It uses a pay-per-use utility model with dynamic elasticity, delivering processing power right over the internet, while a third-party provider manages the physical data center.
There's a great quote from the source material that hits the nail on the head. It says, "The new model of computing says that all kind of computing facilities can be delivered as services, relieving the consumers from the burden of arranging all the stuff themselves." This shift was a total game changer. It meant engineering teams no longer had to act like hardware mechanics. It drastically cut down those upfront investments and gave companies the agility to scale, instantly, on demand, instead of waiting weeks to rack and stack physical servers. So, as we wrap up this explainer, I really want you to reflect on the architecture and the limitations we've just covered. Look at this fundamental engineering question. Why do modern systems move away from traditional computing? Think about the exorbitant upfront costs, the wasted resources during downtime, and that rigid inability to scale. Grasping these specific pain points is absolutely crucial to understanding why modern software engineering looks the way it does today. Keep this in mind as you continue your studies, and thanks so much for joining me.